Hello everyone, let's discuss about alpha beta pruning. Alpha beta pruning is a modified version of minimax algorithm. It is also an optimization technique. As we have seen earlier in minimax algorithm, the number of game states it has to examine are exponential in depth of the tree. Since we cannot eliminate the exponent, but we can cut it to the half. So here we use alpha beta pruning to cut off the search by exploring less number of nodes. Here pruning means cutting off or not visiting the node. So it is more efficient than minimax algorithm. Also, for minimax algorithm, the time complexity or space complexity is b power d. For alpha beta pruning, it is b power d by 2. So it is an optimized version. So here alpha is nothing but the max and beta is nothing but the min. So in the tree we have max first, then min, then max and min. So it is sequential. So first we just go to the last node, like the leaf node, and then we backtrack and find the utility values for every node. So here first the leaf node value is 2. Here the optimal value is 2. So here we keep 2 as the maximum value. Then we visit node 3 and later we update the value with 3 as alpha should be the maximum value. So 2 is less than 3, here the maximum value will be 3, which is given to alpha. Then next, as alpha value is 3, then we keep here the value of 3. Now we visit to the this leaf node and here the value is 5. So here we keep the value 5. But as we said, alpha should be greater than or equals to 5. But here we consider that beta is less than or equals to 3. So here we can't go to this node, like it is unnecessary to go to this node and check if there is any value less than or equals to 3. As here we are saying the maximum node is 5, we have anything that is greater than 5 or less than 5. But here in this node we are considering beta value as less than 3. So it is not necessary to visit this node. Then later, if we see this node, like here we keep alpha is greater than or equals to 3. Here we will be visiting the nodes which will give alpha value greater than or equals to 3. So here we go to this node and we keep it as 0. As we need the maximum value, we check with 1. As 1 is greater than 0, we replace it with 1. Here alpha value is greater than or equals to 1. We update the value 1 here also. Now beta is less than or equals to 1. So we will only update the beta value when the other nodes will be less than or equals to 1. So here we go to 7. As 7 is not less than 1, here we doesn't even need to check these nodes. So now this is the final game tree which is showing the nodes which are computed and the nodes which are not computed. And then the optimal value for the maximizer is 3 in this example. Now let's see about search algorithms. Artificial intelligence is a study of building agents that act rationally. Most of the time these agents perform some kind of search algorithms in the background in order to achieve their task. So in order to achieve or perform any type of task, search algorithms are necessary. So we have two major types of search algorithms: uninformed search algorithms and informed search. Uninformed search is also called as blind search, because in uninformed search the agent doesn't have any background knowledge. It only takes the situations into the consideration and works on it. But in informed search it has some background knowledge and works based on those. So in uninformed search we have different types. It is breadth first search, depth first search, uniform cost search, limited DFS, iterative deepening DFS, and bidirectional search. In informed search algorithms we have three types: greedy search, A star search, and memory bound A star. Let's see about breadth first. Breadth first search algorithm is used for traversing or searching tree or in a graph. So basically it starts at the root node and then explores all the neighbor nodes at the present depth prior to moving on to nodes at next depth. So BFS travels in a level wise. So first it travels the level 1 and then it explores all the nodes and then only it goes to the next level. So it uses queue, so first in first out search. So here let's take an example for BFS. There is an path from S to G using different nodes. So BFS always takes the lesser nodes one, so the minimal ones. So here the path that is chosen by using BFS algorithm is this SDG. So it goes level wise, and then it also considers the minimum number of nodes. Here the time complexity for BFS is order of n power d, where d is the depth and n is the branching factor, and space complexity is order of n into d. Let's see about DFS. DFS is depth first search. It is also used for traversing or searching tree or graph similar to BFS, but the only difference is in DFS it explores all the paths along a single direction, and then if it doesn't find any possible solution, then it goes back to the before step. So but in BFS we go it level wise. In DFS we use backtracking. So it starts at root node and explores as far as possible along each branch before backtracking. If at all it finds a solution, then it doesn't take any backtracking step. So in DFS we use stack, which is last in first out technique. Here there's an example to reach from S to final node G. So in DFS it will be choosing a path like S to A, next A to B, B to C, and C to G. But as we saw in BFS, it takes this path as the final solution, but in DFS it takes this path, and it doesn't go any level wise technique, and it uses backtracking. Here the time complexity is same as in BFS, order of n to the power of d, but here d is the maximum depth and n is the branching factor, and space complexity is order of n into d. Thank you.